This is Unit 3G. It deals with Newton's first two laws, and it also looks at how they apply to terminal velocity and skydivers in particular. So what we have in front of us is four key situations that describe the relationship between force and motion. Now Sir Isaac Newton, came up with three key laws, and we deal with two of them here. The first law tells you about balanced forces, and it says objects do not accelerate when forces are balanced. The second law says that when forces are unbalanced, objects do accelerate. So remember, acceleration is changing velocity. When objects are stationary, it's quite easy to understand what's going on. This surprises nobody that this situation, the object just remains where it is. An object at rest remains at rest. Equally, an object at rest starts to move when the forces are unbalanced. And again, this tallies quite happily with our common sense. What doesn't tally so easily with our common sense is when the object's already moving. Now here, when the forces are balanced, an object in motion remains in motion, which is difficult for us to understand because very often this force is friction, usually from the air, which is not at all obvious. And somehow we feel that these two forces cancel out. And in a sense they do cancel out, but that doesn't necessarily result in no motion. It results in no acceleration, which is what we said at the top here. Now this fourth situation, we have a moving object again. Now the speeding up is in green because we find that quite easy to understand. It's just really an elaboration of the top situation here. So there's the object. Alright, it's going to be moving. There we go. And it's just going to move faster and faster. So it speeds up. What we find harder to understand is if the direction is to the left, but the force is to the right. And really, all this is doing is slowing down, as we've said, but people find this harder to understand. So four situations, two laws, and we have stationary and we have moving. And probably the hardest one to understand is this one here. So let's look at that in a little detail. So here we have one possible situation, and it's the situation we find easiest to understand. We have balanced forces and we have no acceleration. We happen to have no motion in this case, but it's not the most fundamental thing. No acceleration is the most fundamental thing. So equally, or just as easily, we could have a steady speed upwards. Remember, it couldn't be accelerating. Or equally, we could have a steady speed downwards. So no acceleration, not no motion. So we said we'd apply to terminal velocity and skydivers. So starting at the bottom here, we have matter, which has this property mass, and it's a weird fact of the universe that all matter attracts all other matter all the time. And if we have a significant mass, such as the Earth's, we have a gravity field around that. And if we place the skydiver's mass, in this case, in the Earth's gravitational field, we get a force called weight. So we've got weight there. It's a combination of mass and the Earth's gravity. We also have another force in this situation. There we are, there's the red line, which is drag, which is the air crashing into the skydiver or the skydiver crashing into the air. And this can change in two ways. As we can see, this is variable. The weight doesn't change during the course of a skydive, but drag does. And it can do so for two reasons. It could be because of an increase in speed, or it could be an increase in surface area. And we're thinking here of the parachute, obviously. Now, these two forces combine to give us a resultant force, which determines the acceleration. And we have three basic situations. The weight could be bigger than the drag. They could be exactly the same. Or the drag could be bigger than the weight. So let's have a look at the consequences of that. The most obvious situation when we first start, weight is bigger than drag because speed is low, and we're going to get acceleration. So you jump out of a plane, you accelerate. Fairly obvious. We then get this situation where as the speed gets higher and higher, the drag gets bigger and bigger until they equal, and we get constant downwards motion, no acceleration. We do not get the skydiver hanging in midair. And finally, when we open the parachute, we get the situation where the drag is bigger because the area is increased, and we get deceleration, and then we actually get a new terminal velocity. So if we look at that on the graph, we have a fair amount going on here. We've got zero force and we've got a negative force here, so it's downwards, and plus gives us the upwards direction. So throughout this skydive we've said weight doesn't change, so this red line won't change, but we do have drag changing because the speed is increasing here, and therefore we have the resultant changing. So to begin with, it's strongly downwards, and it gets less and less and less as the drag increases until we get to this situation here where the two equal 0. They cancel out, so there is no acceleration. We then get this sharp peak here, which we'll get back in a second, where the parachute opens and the area increases. So now dramatically and very quickly drag increases. This means that the speed decreases until we get the two things equaling out again, weight and drag. So there we are, there's the peak, very rapid deceleration over a few seconds, and again we get our resultant back to 0, and we then get constant speed again where you float safely down to Earth. So there we have it, terminal velocity, quite complicated, could well be a 6-mark question. Key thing to realize is we've got two forces, weight doesn't change, drag is the other force. It does change. It changes for two reasons, either because speed is increasing or because area is increasing. We get our resultant force, and then we get our three kinds of behavior. We get acceleration, we get no acceleration, and we get deceleration.